So we now can move on to our last talk before lunch. And this is Claire Singleton. Claire Singleton is from Strathclyde and is a second year statistics PhD student. And she's going to talk to us about adverse event risk prediction. Claire.
Great, thank you for the introduction. The slides up. Can we see that okay?
Yes, thank you.
Yeah, great, thank you very much. Yeah, so I'm Claire Singleton from the University of Strathclyde, but this PhD is in collaboration with colleagues at King's College London, Professor Laura McGee and Peter von Dadelsen. So my research involves predicting the risk of adverse outcomes in pregnancies that are complicated with pre-eclampsia. And today I'm going to be presenting a piece of research that's investigating if a deep neural network model, so this is a more complex machine learning approach, can exist on existing prediction models. So I'm going to go to the next. There we go. Okay. So you're all aware with pre-eclampsia and that it's one of the most dangerous hypertensive disorders of pregnancy because it can lead to some really severe adverse outcomes for both mother and fetus. I'm going to be focusing on the adverse outcomes that relate to the mother. These adverse outcomes are disproportionately borne by low and middle income countries. And they can affect all of the target organ systems. So it's things like stroke, seizures, hepatic dysfunction, renal failure, placental abruption. That's just to name a few. So the ones that I'll be focusing on comprise a composite called the Peers composite outcome. So this is about 20 of those outcomes that I've just mentioned there. So that's my outcome of interest, these adverse complications that can arise as a result of preeclampsia. So the idea of creating one of these risk prediction models is that we take in health data that's routinely collected. So that's things like your demographics, your blood pressure, proteinuria, some other lab test results. This data feeds into a machine learning model. The model applies its formulas and outputs a predicted probability. These predicted probabilities can then be stratified into risk groups. So we've got very high and high, which can be used to rule in women that are at risk of having an adverse outcome. We've got the low and very low risk group, conversely, to rule out those not at risk of having an adverse outcome. And then we've got the moderate risk group, which is a bit more uninformative. The medical professional that's using this model can then interpret these risk stratification results and use that in conjunction with their own professional opinion to guide decision making and decisions about resource allocation and how to manage these preeclamptic women. The existing machine learning model that does this is Peers ML. So it's an 18 variable random forest model. So it's 18 variables that go in, random forest is applied, and it outputs into these 5 risk groups. So what I'm trying to do is seeing if increasing the complexity of this machine learning approach, so in my case, I'm going to be applying a deep neural network, can that improve both discriminatory ability, so that's the risk group stratification, but also clinical utility. So to do this, the model was developed with a data set of 8,788 women, and these women were from a mixture of low, middle, high income settings, and across 11 countries. So these 8,788 women all had preeclampsia, and it was split into 75% of them were going into the model development, so that's the training data set, and then the other 25% was reserved for both validation and testing. So the training data set determined the relevant predictive variables that we'd want to include in the model. We started off with 32 candidate predictive variables, but with using both clinical expertise and Shapley additive explanation values, it's a variable selection process used in machine learning. We narrowed that down to 9 predictor variables to make the model a bit more pragmatic. With these 9 predictor variables, they underwent multiple imputation because medical clinical data is not always complete, but for the model to work, you need to have a value for each of the variables. These multiple imputed data sets were then used to train this neural network model. Once the model was trained, the validation set was used to determine these risk groups. So the neural network model outputs a probability. So we use this validation set to determine at what probability should this be stratified into the very high risk group, into the high risk group, low and very low. And these thresholds were driven by likelihood ratios such that a likelihood ratio of 10 and 5 corresponded to very high and high, and then negative likelihood ratio of 0.2 and 0.1 to low and very low. And with that model developed with the corresponding risk groups, we could then evaluate it on the reserve portion, which is the testing data set. So just a little overview about what neural networks are to take the lid off the black box for those that aren't familiar with them. The top layer that we've got here in blue consists of input variables. So each of these circles represent input nodes, input variables. These are our 9 variables that we selected to be included in the model. So it's things like their gestational age on admission, their platelet count, their creatinine levels. All of those 9 variables make up our input variables. And these input variables feed into the neural network. In the yellow box, we've got the hidden layers. So this first row represents the first hidden layer. Neural networks can have multiple layers, they can have multiple neurons, but for now I'm just demonstrating it with 2 hidden layers. At each of the neurons in the hidden layer, it uses all of the previous variables as input. It applies a linear predictor of these, so that's a coefficient with the variable, add an intercept, and then it applies some function. The reason we apply some function is so that we can model nonlinear relationships. So this happens at each of these neurons, interchangeable, and then these feed in to the next layer. So the previous layer is used as input to the following layer, so on through as many layers as there are until we get to an output probability, which takes in the input from the last hidden layer. So this output node applies a sigmoid in the same way that a logistic regression is applied, so that we get a predicted probability between 0 and 1. And this is the probability of experiencing an adverse maternal outcome within 48 hours of being admitted with preeclampsia. So it takes your data at time of admission and then gives you a prediction how at risk you are of having an adverse maternal outcome within 48 hours. So our developed model is called PEERS-NN, PEERS Neural Network, and we're comparing it against this PEERS-ML, which was the existing state-of-the-art current model. So PEERS-NN at the top, you can see the women stratified into each group, similar for PEERS-ML below. You'll notice that there are less women stratified to the moderate risk group in PEERS-NN, which is the uninformative risk group where we can't rule in nor rule out. And if we look at this column here, the third one, you'll see that the outcome rates are quite similar for both ruling in and ruling out when comparing PEERS-NN and PEERS-ML. Similarly, the likelihood ratios show signs of good discriminatory ability. The positive likelihood ratio, we'd like that to be greater than 10 for the very high, greater than 5 for the high, less than 0.2 for the low, and less than 0.1 for the very low. This isn't perfect, but also the 95% confidence intervals do span that range of 0.2. So overall, the discriminatory ability is quite comparable between the developed deep neural network, PEERS-NN, and the existing PEERS-ML. So as we've said, discriminatory ability-wise, both models show good signs of being able to rule out women who aren't at risk of having an adverse outcome, and also rule in the women who are at risk of having an adverse outcome. So that can be used to aid clinical decision making about how to manage the level of care and the level of monitoring that these women need. The advantage of PEERS-NN here was that less of the women were stratified to this moderate uninformative risk group. When we turn our attention to clinical utility, that's where PEERS-NN starts to stand out a bit more. So due to its added complexity, we were able to narrow the variables down to just 9 variables. Compared that with PEERS-ML, which required 18 variables. In PEERS-ML, 18 of those variables were lab tests, whereas PEERS-NN, the developed neural network, only required 3 lab test variables. So this is particularly important because resource-constrained settings may find Peers NN to have more clinical utility, because if these lab test variables are hard to source, expensive to use, it means that they can focus their attention on just collecting the data for these 3 specific lab test variables, and then the other 6 variables which were a bit more routinely collected, compared to the use of Peers ML, which is a bit more demanding resource-wise. So in developing Peers NN, we've harnessed the powers of the deep neural network to pick up complex relationships within these 9 variables. And we've done this with fewer variables compared to Peers ML. So we think that Peers NN may stand as a pragmatic alternative to the existing Peers ML. That's everything. Thank you for listening.
Claire, thank you very much. A very complicated subject, which you've done a great job at explaining. And thank you for leaving that last slide up, because that to me is the important one, which shows that for the same outcome, as in, if I've understood this correctly, that whether you use Peers ML or Peers NN, they are similarly useful, but Peers NN is an easier to use system once you've got it set up, because you'll need to put less data in to get an equally useful answer. Have I got that right?
Exactly, yeah, that's exactly it.
Which I think is just as useful in a high resource as it is in a low resource setting, on the basis that there really isn't such a thing as a high resource setting. Certainly in the UK, we wouldn't consider ourselves in the NHS to be high resource. So that's really very useful. So thank you. How long do you think it will be before this is actually usable?
We're currently in the process of making it into a paper. I really don't know. It depends what route you take it. If you go the online open to research available tool, or if we want to validate it more in different places, I really can't tell where the teams want to push it just now.
And eventually, when it's usable, this won't be something that will need a special computer, I'm assuming.
So right now I've trained it all on a MacBook, so I don't think it's too resource heavy, as some other machine learning is often flawed for. The model's all there, it's all trained, so it's just a case of where to put it so that people can use it.
Thank you. That's really, really very exciting. Thank you very much indeed. Jimmy.
Yes, thank you very much. And I've always been fascinated by neural networks, and having done some work in them before. What I was going to ask, though, is that this is a movable feast, preeclampsia. New tests come in all the time, and so on. How how readily adaptable is it to a new test coming along with certain values? Can you rerun the model and to add that to fairly quickly, or would it need a whole range of the same level of work that you've done so far?
That's a really good question. Yeah, so that's kind of one of the next things that I'm hoping to do if there is data available. For example, looking at the PLGF tests with neural networks, this basic structure has been trained up so far. So by training, I mean determining the coefficients. So that's the parameters, which are the coefficients in the intercept. That's all been trained up for these 9 variables. If you have enough data, and I think in this case it'll be a couple thousand maybe, you can take this starting point, add in this other variable, as long as you have the existing 9 variable, as long as you have information about the existing 9 variables as well as this new variable that you're adding, it can just be a case of retraining it on another couple thousand data observations. So it shouldn't be that long of a process.
So can I ask then, is that if you have a new variable that you're going to add, you don't need to have the same parameters alongside the new variable in the same patients? It can be a completely separate study which looks at substance rhubarb and its outcome. It could be slotted in, or do you need to have substance rhubarb along with all the other ones you already measured?
Sorry, no, yeah. So you need to have the existing 9 variables. You need to have the the variables that are already considered in the model, plus this additional one that you would want to. That's my understanding of it so far. If not, there might be another way around it, but that's my thought process at the moment.
Thank you very much. I think that we haven't got any further questions. So thank you very much, Claire, for a fantastic ending to our morning session.